All right. So I need to move this over to the side. Here we go. All right, this problem says, what is the reaction showing solid manganese 2 carbonate trying to dissolve in water? And remember, I'm missing that Roman numeral 2, so please make sure that you put that Roman numeral 2 right in there. Okay? So what does this look like? Well, solid on the left, his ions on the right. Let's do it. On your piece of paper, question number 1, solid on the left, ions on the right. So his ions are Mn plus 2 and CO3 minus 2. Now here's the nice thing about all of the reactions in this chapter. They all look just like that. Only difference is the charges and the coefficients. But everything else is the same, solid on the left, his ions on the right. And what we're saying is, here's an insoluble ionic compound that is trying to dissolve. Even though he's insoluble, he's trying to see if he can get a few of his ions to fall through the cracks. Okay. What is the KSP expression for this reaction? Now, let's make sure we put in states. That's a solid, and I don't have to label these as aqueous because they're showing that they're ions, which implies they're aqueous, but I would like to put in aqueous for you. So Hayden, help me out. Tell me what that KSP expression would look like. So brackets Mn plus 2. Okay. And on the al, you'd have to put that over 1, but for me, you don't. It's understood to be over 1, and that's all that it is. KSP is always going to be equal to the concentration of two things multiplied together. They might have powers. In this case, they don't, because the coefficients are both 1s. Okay. Now, I'm going to show you an ice chart for this fellow. But here's the deal. You're usually not told how much solid you're trying to get to dissolve. We're just going to try to dissolve some big fat spoonful of solid into maybe a liter of water. Okay? So since we're never really told what the amount is that we're trying to get to dissolve, and we know it's not going to dissolve, but a few tiny bits of it are going to fall through the cracks, I like to call it Z amount. I'm going to call it X, so that happens in my C part. You're going to call it Z amount. Could you call it W? Could you call it, I'm trying to think of a letter we don't use. Could you call it D amount? Sure, you could. I just tend to use the last letter of the alphabet and say I have some Z amount. It's a solid, so it doesn't matter anyway, but it is part of stoichiometry. Okay? And so over here, we always put 0 because we're trying to dissolve something in pure water. So we have no ions floating around. Yes?
If you had a large volume of water, would you dissolve that small amount?
It might be able to in a big, large thing, yes. I might.
If you had that volume of this in water,
A teaspoonful, a half a teaspoonful in 5 gallons of water. Maybe so. Yes, maybe so. Okay, now the ice chart, that's the I. Let's write in the C. You ready? What am I going to put, Jordan, at my C? What do I normally put at my C to get to my E, my equilibrium? Minus X, plus X, and plus X. Thank you. You remember to use your coefficients, yes? Remember to use your coefficients, yes? Okay. Now, that means at equilibrium, we have Z minus X, but the X is going to be really small compared to the Z. And then we have 0 plus x. So x compared to 0 is not necessarily small because it's not 0. So I've got to just embrace it as x. Now, what I'm going to be doing in this chapter is I'm always going to be plugging in molarities. I know in gases we didn't because it wasn't always 1 liter, so we left it as moles, but when we get past chapter 13, when I do my ice charts, everything is a molarity value. And particularly when we do this here, we're going to leave everything as molarities. Now, you can have a molarity of the solid, but you're never going to be plugging that in anyway, so don't worry about that one. Okay, this is going to be so small compared to Z, you'll see sometimes squiggly Z written down because the amount of X that does dissolve compared to the big fat Z amount that you dump in, it's not really going to affect the value of Z hardly at all. But because those others are zeros, we do write them down as X's. All right, so that means that if I were to plug in at equilibrium, the KSP at equilibrium, X times X, and these are molarity values, then I would have X squared for my KSP. Agreed? So that means every time you and I come across an insoluble ionic compound where the ratio is 1 to 1, KSP in pure water is going to be equal to X squared. Always, 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 always. As long as the ratio between the two ions is 1 to 1. Okay, so I asked you the question down here that we'll do in a minute. What are some other insoluble ionic compounds that have that same 1 to 1 mole ratio? All right, but before we get there, let's look at number 3. Number 3 says, calculate the KSP for manganese 2 carbonate if 9.31 times 10 to the minus 6 moles per liter are required to make a saturated solution. Now, saturated means to get the solution to be at equilibrium. When you see the word saturated, it means as many ions are present as is allowed. It's reached its equilibrium spot when you have it saturated with ions. It means no more ions are allowed to fall through the cracks. Who says so? KSP. KSP in this chapter is King Daddy. He gets to decide for every single ionic compound how many ions can be floating around together according to his value. All right, so what did they really give me right there then? They gave me X. They gave me the value of X, because look how it reads. Calculate KSP if this many moles per liter are required to make the solution saturated. So they gave me what this is. When the verbiage reads the way it did here, they gave me X. Can I find KSP? Plug and chug, right? So I'm going to come up here and I'm going to say, yes, I can find it. KSP is equal to 9.31 times 10 to the minus 6 squared. Okay, real quick, any other insoluble salts that you can think of that have this same 1 to 1 mole ratio like manganese 2 carbonate does, Hayden? Calcium sulfate has the same 1 to 1 ratio. Calcium sulfate does. All right, Jordan? Yeah. He's white as snow. Silver chloride, good. Okay, one more, Matt. Oh, but that one's not 1 to 1. That one's 1 to 2. I want a 1 to 1. Silver iodide, good. One more, Nyreek. Copper sulfate is soluble. Copper 1 and copper 2 sulfate should be soluble. I need something else that's a 1-to-1 mole relationship, like calcium sulfate, silver chloride, silver iodide, manganese 2 carbonate.
How about strontium sulfate?
Strontium sulfate would work, yes. Strontium sulfate would work. Okay, so do you see what I mean by the fact that they're 1-to-1? Okay, so let me grab my handy dandy eraser real quick, and let's just look up KSP values for those 4 real quick and see who is the least soluble and who is the most soluble out of the ones that you gave me. All right, but I do need a value. Who has the value for the MnCO3 KSP value, that squared? -11, right? Okay. So there's the KSP. What's the KSP for strontium sulfate? I know we had it up here earlier, but I took it away. Thank you. What is it for silver iodide? And what is it for silver chloride? And what is it for calcium sulfate?
You guys suck.
Tyreek, you're trailing. All right. Who's the most soluble of all the choices here, Ira? Okay. Because his value is a larger KSP value, he's more soluble than the others are. All right. Miranda, Mariah, sorry. Miranda is in my other class. Sorry. Mariah, which one is least soluble? Okay, so he is least soluble. Now, quick question. Out of these 2, which one is less soluble? Melissa? Silver iodide. Never mind. Okay, so yes, it would have been that. This one's now least soluble because I forgot that 17, someone did say that, and I wrote 7, least soluble. Okay. Goodness. Well, I was going to try to do, all right, let's just make up 2 numbers. 1.2 times 10 to the minus 6 versus 6.2 times 10 to the minus 6. Out of those KSP values, which one would cause me to say the substance is less soluble? Brianna? Mm-hmm. Okay, this one is less soluble because do we know that if they have the same exponents, then I have to look at this to see who's smaller. We know that because sometimes that negative exponent stuff kind of gets us. All right, I want everybody to look at 5, 6, 7, and 8.